Hey, this is Horner, and we're going to look at 2003 Form B, number one. You have an airplane that is uniformly accelerating from rest. There's a physicist passenger, and they have a string that they're holding. So they're holding it right here, and normally it would hang straight down. So you would see something more like this, and he's put a ring on it. And when the plane accelerates in this direction, the string appears to kind of move back and it holds its position here. She notices that that angle that you have here can kind of help us figure some things out about the airplane. The very first thing that they want us to do, this just looks really complicated and it's just not, so you have to trust me on this one. They just want us to draw a free body diagram to begin with. So let's go ahead and draw our free body diagram for that ring. We know that going straight down should be mass times gravity, and then the only thing acting in this direction is just the tension, and that's it. So you actually get 3 points for this. You get 1 point for tension, 1 point for mg, and you get 1 point for nothing else. That's exactly what the key says. As long as you don't have any other lines on here. And remember, the temptation is to do this. Don't do that. Make sure that you keep everything just as clean as possible on the free body diagrams. When we actually solve for something, that's when we can do more of our lines. But they actually gave a point for not doing anything, which is unusual, I know, but that is the way that it works. For the next part of the problem, it says the plane reaches a takeoff speed of 65 meters per second after accelerating for 30 seconds. So we know our final velocity was 65. We know our original velocity was equal to 0, and the time that it accelerated was 30 seconds. So at this point, they want us to know the minimum length of the runway needed in order to get to that point. So to do that, we've first got to find an acceleration. And remember that acceleration is equal to the change in velocity all over the time period that that occurs. So our change in velocity here will be our final, which is 65, minus our original, all divided by 30 seconds. And so at this point, we end up with 2.17 meters per second squared. So there's our acceleration. You get 1 point so far for this equation, and you get 1 point for plugging everything in and getting the right number answer. At this point, we've got to use an equation in order to find out that distance. Probably the easier one to use is going to be VF squared is equal to VO squared plus 2 times acceleration times the distance. Now we're going to solve for the distance. So our final velocity here was 65. We need to square it. Original velocity was 0. We're going to take 2 times 2.17 times our distance. And now our distance is equal to 975 meters. And that's really all there is to that one. So where do the rest of the points come for this 5-point problem? You get one here, you get one here, and you get one there. And that is it. The next part of the problem, they want us to determine the angle. They want us to determine the angle for that string that the string makes with the vertical during the acceleration of the plane before it leaves the ground. So the plane is still very, very horizontal. It's not nose up or anything. It's just traveling along the ground. They want us to figure what is the angle that the string makes with the vertical. So here we're going to draw this. Oops, let's draw that a little bit better. So we're going to draw a line straight down. We got the string kind of coming back here. They want to know what is this angle right here that it makes. So let's think about for the tension that we have, we've got two components. Okay, we're going to make the components the darker lines this time. We know that there is a tension here, and we've got two sides to our triangle. So we have T times the sine of the angle, because remember this is the opposite side, and we have T times the cosine of the angle. And then remember, our thingy-do is hanging right here, so let's go ahead and draw our two vectors. So there's the tension, and then this one, remember, is mg. And we want to find the angle. So let's go ahead and let's do the sum of the forces in both the y and the x. So the sum of the forces in the x direction are going to be equal to, we've got, well, that's going to be equal to ma. And so the sum of the forces, oops, got to back up here. We're going to have in the x direction t sine of the angle. There's nothing else in this direction, and that should be equal to ma. So at this point, we could say we've got t sine of the angle is equal to ma, and now we need to do the same thing in the y. So sum of the forces in the y direction are equal to 0, and that's because it's not doing anything up and down. It's only accelerating left to right. So sum of the forces in the y direction are equal to 0. This one will be t times the cosine of the angle minus mg is equal to 0. So at this point, we have t cosine of the angle is equal to mg. Now we need to take one of the two sides and set it equal to t. So let's go ahead and do this side since just for fun, I guess. So t is equal to mg over the cosine of the angle. Now we can substitute in what we have for mg cosine of the angle into the t here. So let's go ahead and do that, and let's make this in red. So now we're going to have switch it back over to red here. This will be mg over the cosine of the angle times the sine of the angle over 1 is equal to mass times acceleration. That becomes mg times, so remember sine over cosine is tangent, mg tangent of the angle is equal to ma. And now we can divide both sides by mg, so now we have tangent of the angle is equal to ma over mg. At this point, we can go ahead and just cross off our m's, solve for the angle, so the angle is equal to the inverse tangent of a over g. So at this point now what we can do is plug all our numbers in. We've got inverse tangent. Remember the acceleration we solved for earlier is 2.17. Gravity is 10. And so when you're done, you should end up with an angle, make sure you're in degrees, of 12.2 degrees. And that is the end of 2003 Form B question number 1.